Good day, students. You are once again welcome to yet another of our lecture series on the course Staining and Microbiological Techniques, MCB222. I am Comrade Isaac Igbawua, your course lecturer. And in today's week 2, we are going to consider types of a microscope, or types of microscope generally. And in looking at that, we'll consider the parts of a microscope and their individual uses, or how you use them. Then the operating system of a microscope. We will also look at the magnification and the illumination system of a microscope. Now, types of microscope. Microscopes are of two categories: either light, otherwise optical, and electron microscope, depending upon the principle on which the magnification is based. That is the basis of the classification, whether it is called a light or optical microscope or an electron microscope, depending as to which magnification the microscope can be able to enlarge the image under observation. Now, light microscope, in which the magnification is obtained by a system of optical lenses, uses light waves. The light microscope includes bright field microscopy, dark field microscopy, fluorescence microscopy, and phase contrast microscopy. The individual categories are applicable at different conditions, and different processes are involved while using these categories of microscope. But for the purpose of the routine and general microscopy, we will be considering the bright field compound microscope. Now, the other type is the electron microscopy, or microscope rather, which uses a beam of electrons in place of light waves in the optical type for visualization of objects. These include transmission electron microscopy and the scanning electron microscopy. Now, the light microscope. A light microscope could be a monocular type, which is one-eyed, or a binocular, which are two-eyed or compound microscope. The light microscope forms a magnified image of a specimen, which is based on the principles of absorption, transmission, diffraction, and refraction of light waves. In other words, the light which is hitting the object will be absorbed, transmitted, could be diffracted or refracted, which eventually reaches the eye from where the enlarged image is viewed. Light or optical microscopy involves passing visible light, which is transmitted through or reflected from the sample through a single lens if it is monocular, or multiple lenses if it is binocular, to allow a magnified view of the sample. The resulting image can be detected directly by the eye, imaged on a photographic plate or captured digitally. We, for the purpose of this lecture, be considering the compound microscope. Here we are on the screen, the structure or diagram of a bright field light compound microscope. You can see the base, you can see the arm, you can see the parts as labeled from 1 through 9. Each of the parts has their part, and collectively they, when used correctly, give the product of an enlarged, brighter image, which is viewed as a magnified image, the purpose for the instrument. Now, the parts of a microscope. Number 1, as seen on the instrument, is the eyepiece or the ocular lens, which are responsible for the final magnification of the sample under view. Often 10 times magnification, but can be different. You can have maybe times 7, depending on how much, because as we learned earlier in the first lecture, the final magnification is a product of the objective lens with the magnification of the ocular lens. So when you multiply the two, it gives you the total magnification of the sample under view. So if you are using a times 10, for instance, and you are using a 10 times rather objective, you are having 10 times 10. It means the object is magnified 100 times its original size. Number 2 on the diagram is the revolving nose piece. This is made to hold multiple objective lenses in place. The base of the nose piece can rotate, allowing each of the lenses to be rotated into alignment with the ocular lens or with the eyepiece. Number 3 is the objective lenses. Initial magnification of your specimen, as said earlier, occurs using the objective lens. After the light have from under or reflected from any source hit the specimen or object, upon transmission, it is viewed by the objective lenses, and this is where the initial magnification of the object occurs. Now, most bright field light microscope have 3 or 4 objective lenses seated into the revolving nose piece base. It could be a times 4 times, 10 times, 40 times, and 100 times, or oil immersion objectives, depending on the type of sample you are going to examine. But principally, the lower magnification are used in the initial examination. But most, if not all, stained samples or films are examined using the 100 times or oil immersion objectives. Number 4 on the diagram of a compound microscope is the coarse focusing knob. The larger of the 2 knobs is the coarse adjustment knob, which moves the stage up or down to bring the specimen into focus. In other words, if you have your specimen on the stage and clipped by the mechanical arrangement of the stage, you will have to move the coarse adjustment either up or down to bring the object into focus. Then the fine adjustment, which is number 5 structure of the microscope, is the smaller of the two knobs. The fine adjustment knob brings the specimen into sharp focus, unlike the coarse, which just focuses it and is not fine, it is not bright. This one brings it into sharp focus under low power and is used for all focusing when using high power lenses such as the 100 times oil immersion lens. Numbers 6 and 9, which is stage and mechanical stage respectively, are the horizontal surface where you place the slide onto which the specimen is made and is called the stage on a general note. It could be a stage where it becomes mechanical. It has all the adjustable appliances. The slide is held in place by spring-loaded clips and moved around the stage by turning the geared knobs on the mechanical stage. Number 7 is the illuminator. This contains the light source. It could be a lamp made either of an incandescent tungsten halogen bulb or an LED. There is normally a switch which turns on and off the light source. Some microscopes also are made with a rheostat, which is located on the side so that you can use it to adjust the brightness of the light. If the light is too much, you adjust it to lower it. If it is not so bright, you open it the more to give more light, because the brighter, the more clearer the object and image so formed is viewed. The diaphragm and the condenser. The diaphragm controls the amount of light passing from the illuminator, which is your light source, through the bottom of the slide. There is a small lever used to achieve the optimal lighting. That lever is called the Irish diaphragm. It closes and opens depending on the amount or intensity of light that you want it to pass through. The condenser is a lens system that focuses the light coming up from the illuminator onto the objectives, and so you can take it also up and down depending on which type of sample that is on your stage. If it is stained, you have to take it up and open it fully. If it is just a wet prep, you take it down and you close the Irish diaphragm sufficiently enough to permit the desired light only passing through it. We will be considering the operating system of a microscope, having known the individual parts and the roles or whatever use they have on the instrument. The optical system as one of the operating systems of a microscope. This consists of, in a compound microscope, of two lens systems, one found on the objective lens or lenses and the other on the ocular eyepiece. The objective lens system is found attached to a rotating or revolving nosepiece. This is seen in figure 1, part 2. Figure 1 is the microscope, that compound microscope, and then the part 2 as labeled. A microscope usually has 3 or 4 objectives. The 4 times, 10 times, 40 times, and 100 times objective lenses that differ in their magnification and resolving power. The limit of useful magnification is set by the resolving power of any microscope. Now, this resolution is given by, is given as numerical aperture, abbreviated NA. The numerical aperture is the ratio of the diameter of the lens to its focal length. Magnification of the microscope. This has to do with a process of making an enlarged object appear larger than its original size, as earlier explained. It is the apparent increase in size of an object, and the resolving power is the ability to reveal 2 closely adjacent structural details as if they are separate and distinct, expressed quantitatively as microscope's limit of resolution. What that means is that the resolving power of a microscope is what actually tells whether or not the microscope is good and is sharp, because it has the ability to reveal closely related structural details as if they are lines separate and distinct. If the resolving power is not strong or high, you will see that images will appear so blurred that you cannot be able to distinguish. You can only see them there, but as to whether there is a demarcation between two as 2 separate things, it is not feasible. And so the resolution, which is the limit of resolution of a microscope, is calculated as the wavelength at which the object is divided by 2 times the numerical aperture of the lens of the particular microscope in question. DNA is labeled on the objective. Now, the illuminating system. The objective and ocular lenses can only perform well under optimal illumination conditions. To achieve these conditions, the light from the light source, which could be a bulb from a power supply, electricity, or sun rays, or whatever, depending on the type of microscope, because some monocular uses just a mirror which reflects the sun rays to be sent up, which is viewed in the same manner. And it must be centered on the specimen. The rays so coming are made to hit the specimen under view. The parallel rays, light rays from the light source, are focused on the specimen by the condenser lens system, which moves up and down to affect the focus. The amount of light entering the condenser lens system is adjusted using the condenser diaphragm, as said earlier. The higher the magnification and resolving power of a lens, the more light is needed to view the specimen, and the more light, the brighter, the more details, the better the resolution. At this juncture, I think we also understand in today's lecture that there are 2 types of light microscope. It could be 1 eye or 2 eye, which is a monocular or a binocular, but the operating system is the same thing, where you have the light source coming from under a specimen which is laid on the stage, and mechanically it is adjusted to be in focus, whose rays upon transmission is received by the objective lens, which first enlarged the object, whose image that is real is formed in between the tube just before the ocular lens, which further, upon hitting it, further enlarge the image, which is now visual and inverted. The rays are now directed either by a prism or whichever another mechanism, and directed towards the eye, which views the image as a more enlarged image, several times more than the original size, courtesy of the lenses, objective and ocular lenses. Now with this, we come to the end of today's lecture 2, with the understanding that the microscope is an indispensable instrument, and the workings and how best it can give results has to do with the maintenance and how well the person handling it knows how to go about the instrument, using the instrument. Thank you for the day.